Hello everyone, my name is Elizabeth Spiraki from geoengineer.org. I am pleased to introduce you to April's 2017 online lecture organized by the International Society for Soil Mechanics and Geotechnical Engineering. This month, Professor Leroy will be talking about compressibility and consolidation of clays from lab to field conditions. Professor Serge Leroy obtained his engineering degree from the Institut National des Sciences Appliquées, Lyon, France, in 1970 and his PhD from Université Laval, Quebec, Canada, in 1977. He worked 2 years with the consulting firm Terratech, Montreal, and then joined Université Laval, where he spent his entire career as professor in the Department of Civil and Water Engineering. His main domains of research have been soft clays, microstructured soils, compacted soils, embankments on soft soils and landslides. He was the 1999 ranking lecturer. Note that after the completion of the webinar, Professor Leroy will be happy to answer any questions posted on the ISSMG Q&A platform. The platform will remain active for 2 days. It is located below the present video and you may access it with your GeoWorld account. Enjoy the lecture.
I first would like to acknowledge the International Society of Soil Mechanics and Geotechnical Engineering for inviting me to give this presentation on compressibility and consolidation of clays from lab to field conditions. This is a topic which has been discussed for more than 80 years, but which is still discussed. In fact, the presentation will be divided in 4 sections: introduction, laboratory conditions, field conditions, practical conclusions. And as the introduction, in fact, the problems associated with embankments on soft clays are essentially stability, settlement rates, lateral displacements. In fact, for this presentation, we talk only on settlements and settlement rates, which in other words we'll talk about compressibility and consolidation. Just a few words. Usually, the compressibility of clays is represented in a E log sigma prime V diagram and characterized by the pre-consolidation pressure, which is defined by sigma prime or sigma prime Vy, and essentially the compression index C sub C. With time, in fact, when we load a soil, there is some settlement, some decrease in void ratio associated first to pore pressure dissipation, and that's reconsolidation, but then settlement continues during secondary consolidation. And this secondary consolidation is characterized by C alpha E, which is the slope of the curves in a E log T diagram. In fact, the general equation for one-dimensional consolidation is the one here on the right, and it shows that the strain rate is directly related to the pore pressure, which means that if we have movements, settlements during secondary consolidation, that means that there are still excess pore pressures. They are small, but still there. Laboratory conditions, in fact, Mesri and co-workers have demonstrated that C alpha E is proportional to C sub C for a given clay, Here, the ratio is 0.03 for these two clays. And they also have shown that for inorganic clays in all, in fact, this ratio is always equal to 0.04 plus or minus 0.001. For granular soils, it's smaller, but for organic soils, it is larger. So this is an interesting characteristic. Now a few words about the CRS, constant rate of strain odometer test, because I will refer to this test and maybe some people are not familiar with it. In fact, we have a specimen in a odometer cell, which is loaded on a press, triaxial press, at a constant rate of strain. The objective of this test is to get a compression curve within about 2 days. The advantage of this curve and of this test is that the stress-strain curve is continuous. So the pre-consolidation pressure is well defined. In this test, in fact, we measure the pore pressure at the base of the specimen, UB, and the vertical effective stress is equal to sigma V minus 2/3 of UB. In fact, there are limitations when the pore pressure at the base is too high. What has been shown by several authors is that when we increase the rate of strain, in fact, the compression curve moves towards larger effective stresses as indicated on this figure. Here is about 10 minus 8 second minus 1, and here it's 10 minus 5 second minus 1. So from this kind of set of curves, what we call isotax, which are relevant for stage loading tests as a conventional odometer test, in fact, can be shown that this set of curves here can be described by two curves. One which is showing the log, says the log of the pre-consolidation pressure or vertical yield stress versus strain rate, and a normalized effective stress strain curve in which the vertical effective stress is normalized with respect to the pre-consolidation pressure associated to the strain rate. The slope in the log-log diagram can be defined by alpha. In fact, we can show that alpha is equal to C alpha E over CC. So that's the same thing, which means that for inorganic clays, for example, C alpha or C over CC or alpha is equal to 0.04, typically. What does that mean? That means that, in fact, the change in effective stress when we change the strain rate by 1 order of magnitude is typically 10%. Remember this number. So it's smaller for granular soils and it's larger for organic soils. This is an example on Batiscan clay, and you have here the vertical effect stress or pre-consolidation pressure versus strain rate in log, and alpha is equal to 0.048 in this case. These are, for the same clay, normalized compression curves, and you can see that all the data, except these two data which are being obtained at too large strain rates and which gave too large pore pressures. Otherwise, all the data are in a small range, considering that we are working with a natural clay. This is another example, Berthierville clay, and the curve in the middle here is the relationship between the vertical yield stress and the strain rate at 20 degrees, and here you have the normalized stress-strain curve. In fact, Watabe et al. Have shown that the relationship is not perfectly linear in log-log, but is curved as shown here. And in particular, there would be an asymptote at a pre-consolidation pressure equal to 70% of the pre-consolidation pressure at a strain rate of 10 minus 7 second minus 1. 10 minus 7 is typically the strain rate which is obtained after 24 hours of freezing. So it will be a curve and not linear. In fact, we observe this earlier, and you can see on this data that alpha is equal to 0.04 between typically 10 minus 8 and 10 minus 6, which are strain rates usually obtained in laboratory tests, but that at larger strain rates, the slope is larger and it is smaller at small strain rates. And this is what I just said, and this is consistent with what is shown here. These test results have been obtained by loading specimens in the normally consolidated range and then unloaded it just a bit to a given OCR. When the OCR is relatively small, as 1.5 here, what happens is that after unloading, the soil swells a bit and then starts settling again in secondary consolidation. However, when the OCR is high, for example 8 here, at that time there is swelling due to pore pressure dissipation, and then the soil continues to swell in a kind of secondary swelling. So, in fact, the strain rate model I was talking about before can be generalized in this form here, where we have here secondary consolidation, but below an indifferent equilibrium somewhere here, in fact, we have a secondary swelling. So that means that it's a kind of generalization of the stress-strain rate model. Practical implications of the strain rate model in laboratory conditions. First, if during a CRS test we change the rate of strain, at that time we move from one curve to another curve. And this is shown here where you have two strain rate which have been used, epsilon V1, epsilon dot V2. And so that's logic with the strain rate model. Now, if we come back to the CRS test, I told